So before I even start the chapter, let me clarify that both the aldehydes and the ketones have the same group, and we call this the carbonyl group, right? And by carbonyl group, I simply mean C double bond O as a part of the functional group. Now, if that C double bond O has H on one side and R on the other, that is known as an aldehyde. However, this C double bond O has actually have R groups on both sides. We call that a ketone. So the same carbonyl group is present in both the functional groups. Aldehydes are somewhat different as ketones. Aldehydes are usually at the terminal or the end of the chain because they have hydrogen on one end, and the chain continues from the R side. Ketone, on the other hand, is usually in between the whole chain, maybe at the center, maybe a little on the side, but never at the terminal end because both sides are continuing the carbon chain by R and R groups, right? This is pretty much the introduction of the functional group that we have back from chapter 14. तो इसको रेस करते हैं, आगे चलते हैं. Aromatic या benzene based carbonyl groups बहुत distinctive element like dot रखते हैं. One of them is benzaldehyde. That means कि हमारे पास एक benzene ring है, ठीक है, और उस benzene ring के ऊपर हमारे पास हमारा पूरा एल्डिहाइडिक ग्रुप यानी C डबल बॉन्ड O और H लगा हुआ है. दूसरी तरफ R एक्चुअली ये बेंजीन रिंग है. दिस वन इज बेंजल्डिहाइड. बेंजीन के आगे एल्डिहाइड लगा दिया, बेंजल्डिहाइड. इट्स easier to understand that way. This makes the element essence, the flavoring that we use in some cakes, in some puddings, biscuits, the list goes on. Benzaldehyde is a component of mixtures that smells and flavors of many fruit. It includes mangoes, cherries, apricot, a long list. All right. The structure of heptane 2-on and benzaldehyde are shown in the figure later. More complex aldehydes and ketones occur in common smells and flavors, such as lemony odor of the trinella candles. The trinella candles can repel mosquitoes. It is commonly used in the areas where we have a lot of mosquitoes and a lot of diseases due to those mosquitoes. Now, mosquitoes are really scary these days because they can cause all kind of bad diseases, including malaria, including dengue, and the list goes on. Now, the aldehyde responsible for citronella can be taken out of it. Chemists have also extracted aldehydes from lemongrass and citronella grass. Now, you can see this whole thing in front of you. If you look at it, you understand there is a double bond in there. So there is definitely an alkene part over here. And you have this CHO. Remember, this represents the aldehydes. C double bond OH is written in small form as CHO. So wherever you see as a CHO, that means we're talking about aldehyde. Let's move on. This was just the introduction. Let's go on ahead and let's take a look at this benzaldehyde. As I told you before, heptane 2-on. See, I was telling you that in ketone, this would be a part of the structure being in the center or a little bit onto the side, but never the ending carbon. And in this case, this is always a terminal or the ending carbon. I hope that makes sense. Moving on. Whatever those are used for, that's not the case we're going to study now. What we're going to focus is the more difficult part. So the homologous series. Remember, aldehydes were formed from the oxidation of primary alcohol as well as alkenes. Ketones can be formed from the oxidation of secondary alcohol, again, as well as alkenes. So remember that we have been forming aldehydes and ketones previously. Moving on. Carbonyl group is the C double bond O. It is bonded to carbon atom and a hydrogen atom. Aldehyde, of course, what the aldehydes are named as. Take a look. This is this carbonyl group. I'm going to use a different color that may not be as good visible. Okay, so aldehyde, if I put a hydrogen over here, this methanol. Instead of putting a hydrogen over here, if I put a CH3 over here, right, then this is this atom. Two carbon atoms, at three carbon atoms drop, so on and so forth. This keeps moving on. And remember the CHO that we have been using. So you can see for aldehydes, we are using Al as the suffix, methanol, not methanol. So a single O and a single A changes everything. O, functional group alcohol, homologous series alcohol. A, functional group aldehyde, homologous series aldehyde. So make sure you carefully read or write the names when you're doing that on your paper. Moving on. This one is propanone. Now, how are we putting it? Pretty simple. C double bond O, carbonyl carbon in the center. We have CH3 over here. We have CH3 over here, the smallest groups. So that's how you number them. That's 1, 2, 3, 3. So this is second carbon. So this is propanone. We don't write 2 in it because propanone is always going to be a 2 on. Same goes for butanone. If I put it over here, I have to start numbering from this side. So butanone and propanone are always 2 ohms. However, starting from pentanone, it can be 2 ohm or 3 ohm. Remember, this is 1, 2, and this is 1, 2, 3. In 3, I can start the numbering from either side. In ketones, we replace the E at the end of the alkane, and we name them with a number. And of course, in this case, our suffix is on. This is our suffix. So I hope this gives you the idea how we're going to treat this. Now, in case of ketones, it can never be a 1 on. Remember, 1 on does not exist. So if someone is writing for you propan 1 on, from this one, get the idea that ketones never have number 1 in them. It's not possible. The chain has to be on both sides. All right. So in MCQ options, if there is a 1 on, that's definitely a wrong name. Don't waste your time on that one. I hope this clarifies it. Now this clarifies how we name them or how the structure goes, both for aldehydes, both for ketones. Remember, we have already discussed how they're made. So moving on. Any questions so far? Okay, I assume there are no questions. Moving ahead. Preparation of aldehydes and ketones. Now, preparing aldehydes. We know primary alcohol oxidizing agent will give you aldehyde in water. So we are familiar with this reaction. We can do this with potassium dichromate 6. The orange color will change to green. To make the aldehyde, primary alcohol is heated gently, right? So let's go for a practical activity and understand this. So we have a primary alcohol that we're going to oxidize with the help of acidified oxidizing agent. And remember, the acidified oxidizing agent is added 1 drop at a time to warm primary alcohol. The aldehyde made is distilled off as it forms in the reaction vessel. This method works because the aldehyde product will always have a lower boiling point than the alcohol reactant. If the aldehyde is not distilled, any further heating with this acidified oxidizing agent present will oxidize it into carboxylic acid. Now, don't forget that this was very much possible. We have studied this in 15th chapter as a part of alkenes. We have studied this in chapter number 17 as a part of alcohols. We know that if you're not going to remove the aldehyde out of your system, it's going to be oxidized into a carboxylic acid. Take a look at the picture. This is how it goes. So we have ethanol plus we have acidified potassium dichromate 6 We give it a gentle heat. Don't forget, acidified means we have some dilute sulfuric acid in there. It can also be phosphoric acid, but we prefer sulfuric acid. And we keep distilling it out over here as ethanol. Remember, he has already told you that the product, aldehyde, will have a lower boiling point than alcohol. Okay, moving on. Remember, the aqueous ethanol forms smells like rotting apples. This is a pretty good tip for paper 3. Moving on, ketones. We're going to do the same, but with secondary alcohol, right? To produce a ketone, this acidified oxidizing agent must be heated with a secondary alcohol, not just warmed, heated. The color changes from orange to green. Unlike aldehydes, ketones cannot be further oxidized, so you can heat the reaction mixture under a flux, add excess oxidizing agent. We do not need to distill off the product immediately. This would form a ketone definitely. That's easy. That's why we don't even have a diagram for this one. Moving on to the next part, reduction. Reduction of aldehydes and ketones. This is the first reaction, sort of reaction that we go for. Okay, so in this case, aldehydes can have reducing agents. They would be converted into primary alcohols. Ketones acting with reducing agents would be converted into secondary alcohol. I've already given you idea about this one. This shouldn't be difficult. So the reducing agent we normally use is an aqueous alkaline solution of sodium tetrahydroborate, NaBH4, or LiAlH4 in dry ether. NaBH4 can be used in aqueous alkaline system. That's how it works. It activates. It does not react explosively with water, being a less stronger reducing agent. So yeah, you can work with water. In case of LiAlH4, it is a far stronger reducing agent. It definitely reacts explosively with water, so we use it in non-aqueous conditions. Now, reduction reaction carried out by either warming the aldehyde or the ketone with this one, or add LiAlH4 dissolved in dried ether. You can use diethyl ether. Now, the name diethyl ether means C2H5 is connected with O, connected with C2H5, ethyl, so diethyl, and O stands for ether. At room temperature, the organic solvent has to be dry because this is a more powerful reducing agent than NaBH4 and reacts vigorously with water. Just like we used O with oxidation, we use H with reduction. That's how the reduction goes. Primary into aldehydes into a primary alcohol, ketones into a secondary alcohol. That's how easy it is. Since we have studied the cycles before, this shouldn't be a problem. Moving on. Now the nucleophilic addition. The addition reactions so far have electrophilic addition. This is different. Remember, the previous ones had electrophilic addition because we were talking about carbon-carbon double bond in alkene molecules, as he have mentioned. This time, we're going to go for nucleophilic addition. Now, why are we joining the word nucleophilic in addition? Now, remember, as soon as I use the word addition, it means it's going to give you a single product. Remember, all addition reactions give you a single product. As soon as I use the word nucleophilic, that means a nucleophile is going to initiate this reaction. So, with this kind of explanation, you'll have your mind made that what's going to happen. Both aldehyde and ketones undergo these addition reactions with hydrogen cyanide. Addition of HCN takes place across the C double bond O portion, of course, wherever the double bond lies. And the attack by a nucleophile is by a nucleophile, not an electrophile. That's for the difference. I've already gated that part, so let's move on. So nucleophilic addition reaction for aldehyde propanol when heated with HCN. Remember, HCN is something that we never use directly. We always generate it in situ. We generate it or produce it in the reaction vessel. How? We use KCN and we use dilute sulfuric acid. We have been doing it every single time in the previous example. We used HCN before with alkenes for electrophilic addition. So we have discussed it previously as well. We did the same in situ production. So as soon as we go with this, now remember, in this case, what happens is that the C double bond O would be converted into this product. Now, how do we do this? Just a second. Let me see if we have a mechanism. Yeah, great. We have a mechanism here. So I'm going to go back to the example, this example, after we are done with the mechanism, because you'll understand how HCN is added to it. All right. Let's go with the mechanism first. Mechanism of nucleophilic addition. Now remember, this is going to be extremely easy because you're already familiar with nucleophilic substitution. It starts like substitution, but then there is addition because the addition is possible because of the double bond throughout the molecule. Now, as cyanide is a negatively charged species, a nucleophile, right? It can attack the partially positively charged center. Now remember, this is carbon and oxygen. Oxygen has a higher electronegativity than carbon. So carbon is partially positively charged, oxygen is partially negatively charged. Now, when the CN attacks carbon, one of the bonds, not both the bonds, one of the bonds move on oxygen. So the CN get attached to carbon in an intermediate, and oxygen has the negative charge because of the bond moving on to oxygen. And now carbon and oxygen are singly bonded, not doubly bonded anymore. This intermediate can further attack on an HCN molecule. How? Oxygen is negatively charged. In HCN, hydrogen is partially positively charged, and this entire HCN is partially negatively charged. Oxygen can clearly or easily attack the partially positive center. The bond then moves on to CN, producing for us the nucleophile in step 2. So you have the CN attached to carbon, and that carbon oxygen is now converted into an alcohol. So we have 2 hydroxynitrile. The CN carbon gets number 1, the original carbon gets number 2. This number 2 carbon has an alcohol group attached to it and a nitrile group attached to it. Nitrile gets the preference to have the suffix in the name, hence number 1. OH does not get the preference, so we can't use ol. We can't use ol. So what do? We use hydroxy. This should give you the idea. When alcohol has preference in the name, right? Then what happens? Then we use the suffix ol. When alcohol has no preference, right? What do we use? We use hydroxy. Now this is a suffix and used at the end of the name. This is a prefix usually used in the middle or the start of the name. Mostly not at the start of the name, but the middle of the name. Or even if it's present at the start of the name, the number would always be before it. So it gives you 2 hydroxynitrile products. Okay, so moving on. In step 2, this happens. So all aldehydes and ketones form 2 hydroxynitrile products. Why are we using aldehydes and ketones? Now remember, there are 2 bonds over here, this one and this one. If one of them is H and one of them is R, this would be an aldehyde forming 2 hydroxynitrile. If both of them are R's, it would be a ketone forming 2 hydroxynitrile. So it doesn't really matter what carbon previously had on both of its bonds, whether it was hydrogen or it was an R alkyl group, they can undergo nucleophilic reaction, a nucleophilic addition reaction, and the OH will become the hydroxy group, and that's on the adjacent carbon to the nitrile group. Remember, don't forget, because of the nitrile, number of carbon atoms in the chain would be now greater. One step greater. Remember, whenever you use nitrile, the length of the chain increases by 1. Okay, I hope you get it. Now, starting with aldehyde methanol, the hydroxynitrile formed in a nucleophilic addition will be hydroxyethane nitrile. Okay, now let's clarify it. No, it's not here, so let's get back. Okay, we are working with propanol over here. Now we started with prop, but now we have 2-hydroxybutane nitrile. So prop was converted into bute. Since it's 2-hydroxynitrile, it should be really easy how that works. Now let's get an idea from it. 2 means that this carbon is 1, this carbon is 2. Hydroxy means we have an alcohol group. Bute means there are a total of 4 carbon atoms. Ene means those carbon atoms are singly bonded. Nitrile means the first carbon atom has a triply bonded nitrogen. Hence, 2-hydroxybutane nitrile. All right. So the names are pretty easy with aldehydes. How? You take the initial part of the name, 2-hydroxy, and this part is converted into an alkane right in the middle of the name. That's how easy it is. For example, if it was ethanol, how would you write the name then? It would be converted into 2-hydroxy. It would remain the same. Now, after this 2-hydroxy in between the nitrile parts, 2-hydroxynitrile has to be there. Now, this eth would be converted into prop. So propane nitrile. That's how it goes. That's how easy it is to convert an aldehyde into a name. Unfortunately, if you're talking about a ketone, we definitely need to take an example of ketone because he winds up the process, this whole thing, right after this topic, right after the mechanism, as you've seen with me. We have the mechanism up next, and after the mechanism, there are questions, and they haven't given us any examples. So let's take an example of a ketone working with us. Now, I'll write the aldehydes and ketones in a similar way. The C double bond O gives you a clear idea which 2 bonds were and how we can convert this O into OH later on, and the C would have CN added to it. So CH3, C, double B bonded O, CH3, and remember this is propanone. It has 3 carbon atoms. They are singly bonded and on because we have a ketone over here as a functional group. So when it reacts with HCN, right, what happens? CN goes in first, attacking on the carbon atom. This bond goes on oxygen, which then takes this hydrogen to form the alcohol. So I tend to write it a little bit differently. CH3, C, OH, CN, CH3, like this. I sometimes tilt it, that's fine. If you write it like this, if you write it like this, does not really matter. Now all 3 carbons are in the chain, right? If I wrote like this, it would be a horizontal working. This carbon would always be 1, 2, 3. So now how would we write it? Now in this case, this prop would remain the same. Why? Because this prop because of 3 carbon atoms in a chain. One of these carbon atoms move out of the chain because we include only one as a part of the chain. And remember to include the bigger end of the chain in this one. Okay. I mean, if it has methyl on one end and ethyl on one end, make sure you add ethyl to the part of the chain. That's how you'd get the longest chain. Okay. So this is going to be 2-methyl, 2-hydroxy, and propane nitrile. That's how I would name it. So in ketones, not only the chain usually tends to remain the same, or it changes, of course, if you would have bigger part over here and a smaller part over here, that smaller part would be taken out. It may be a step down as well. Okay, so expect anything because bigger ketones work slightly differently than propanone. Also, asymmetric ketones work differently than the symmetric ones. So 2-methyl, but something definitely is that we'll always have a branch on this chain in case of ketones. So 2-methyl 2-hydroxypropane nitrile. 2, because on this second carbon we have a methyl group. 2, on this we have the alcohol part, so hydroxy. Prop, because there are 3 carbon atoms in the parent chain. Ene, because they are singly bonded. And nitrile, because the first carbon atom has triply bonded nitrogen to it. Hence the whole name. Now, this reaction is particularly useful to increase the carbon chain length by the original aldehyde molecule by 1 carbon atom. This only works for the aldehyde molecule. This usually doesn't work for ketones, so that's why he has been specifically talking about aldehydes over here. However, past papers do have these reactions with either aldehydes or ketones. Now remember, the nitrile group can easily be hydrolyzed to carboxylic acid. How? Acidic hydrolysis. Whatever we have over the chain over here, it would be converted into a carboxylic acid. You can also hydrolyze the nitrile group by refluxing with dilute alkene. Now this adds something to the previous detail. Now you are familiar with this reaction already from the previous chapter. We did this, but we never did this specific part of the detail. These 3 lines have been examined in past 5 years a lot, really a lot. So instead of going with acidic hydrolysis, if we go with alkaline hydrolysis, the product would be somewhat different. Yeah, we definitely would get NH4Cl, but we won't get carboxylic acid, we'll get sodium salt. All right. So sodium salt of carboxylic acid, if you want to produce the carboxylic acid, the products are treated with a strong acid, such as dilute sulfuric acid. Okay, you can again convert it into a carboxylic acid. How? Treat it with a strong acid, and this would be converted into a carboxylic acid. The sodium would be easily replaced because of the presence of a strong acid. This is an extra step. Even after getting the sodium salt of the carboxylic acid, you can still convert it back into acid by doing this reaction. I hope it gives the idea correctly. So remember this part as a whole. These have been used in past 5 years papers a lot. Any questions from that part? This whole nucleophilic addition has been in past papers a lot, so make sure you understand nucleophilic addition for both aldehydes and ketones, along with the mechanism, along with the further hydrolysis for conversion to carboxylic acids or their sodium salts, be it acidic hydrolysis or alkaline. So any questions? All right, I assume there are no questions. Moving forward, testing for aldehydes and ketones. As in our previous chapters, I told you that we'll have tests for both aldehydes and ketones. So testing them gives us the idea. Why do we test them? Since they have the same carbonyl group and they are both the subparts of the same carbonyl group, we need to test them. The testing makes it easier for us to understand how aldehydes and ketones work because the reactions we studied previously, take an example of forming a nitrile from them. Both aldehydes and ketones give the same reaction. So you won't be able to differentiate. Moving back, reduction, both aldehydes and ketones can be reduced. So again, the reaction goes for both of them. So it's really difficult for us to differentiate between them, and we can't do it without tests. That's why the chemical testing to exactly distinguishing between them, differentiating between them, or identifying one of them is really important for us. So starting with the test for the carbonyl group. The first test is pretty easy since we're going to just test whether the carbonyl group is present or not. So both aldehydes and ketones are going to give this test positive since both have the carbonyl group present in them. When I use the term carbonyl group, I simply mean C-O. It really does not matter what is connected to the carbon. This inner part is the carbonyl group, right? So the reaction of aldehyde and ketone with 2,4-dinitrophenylhydrazine, we are commonly going to call it 2,4-DNPH, dinitrophenylhydrazine. Let's clarify. 2 and 4 because this is 2 position, this is 4, sorry, this is 2 position, this is 4 position, this is position 1. Dinitro because there are 2 NO2 groups, NO2 is nitro group. Phenyl because of the presence of benzene ring. Hydrazine is actually NH2 connected to NH2. Hydrazine basically itself is N2H4, but since we are connecting hydrogen over here, so one of the nitrogens lose a hydrogen, and that's how benzene and them are connected. So it becomes N2H3, in fact. So you can see 2 hydrogen over here, 1 hydrogen over here. That's how we connect the benzene ring and the hydrogen. So 2,4-dinitrophenylhydrazine. That's how the name goes. Now, every time they're going to either react with an aldehyde or a ketone, they're going to go for the reaction positively. Why? Because they have the carbonyl group. Now, this is more like a condensation reaction. This H2 from the hydrogen and this oxygen from the carbonyl group are always going to form water, and the rest would combine to give us 2,4-dinitrophenylhydrazone. It's known as 2,4-dinitrophenylhydrazone. No matter what compounds, what parts on the carbonyl carbon we have over here, it's pretty easy. So every time you go with this reaction and you have a product over here, the product can be different with different aldehydes or different ketones, but that's how you name it, 2,4-dinitrophenylhydrazone, which means there is something connected to the hydrogen part. And of course, this H2 and this O is going to give us water. Atoms lost in condensation reaction to form water. Remember, condensation reaction gives you a bigger product, along with that, a small stable molecule. Hence the idea of this. So other classes of organic compounds that also contain the carbonyl group, such as carboxylic acids and esters, they also contain this part. Carboxylic acid consists this part because of the whole structure. Now, esters consist of this part because of the whole structure, okay? But they both don't give 2,4-dinitrophenylhydrazone reaction. Now, what do this exactly does? What is the observation? Let's talk about the observation. So testing with 2,4-D and pH, if we add it to aldehyde or ketone, we get a deep orange precipitate. This precipitate gives us the idea of the 2,4-D and pH test being positive. Now, there is one simple line which is important for paper 2 and paper 3. The precipitate can be purified by recrystallization. Its melting point can be measured experimentally, and we can refer it to the melting point data, and we can identify the specific aldehyde or ketone used in the test. Because based on what kind of chain is going to get connected over here gives us the specific melting point data. So we can always go for the fingerprinting technique for this one. Remember, if you refer anything to the melting point data or any kind of data like that, we call it a fingerprinting technique, which means whatever we get, we are going to somehow observe it with a physical or a chemical, usually with a physical test, and compare it with the data at hand. So deep orange precipitates, they're really beautiful in lab. Okay, distinguishing between aldehydes and ketones. Now, once you have confirmed the presence of a carbonyl group, which only goes positive with aldehydes and ketones, not with carboxylic acids or esters, you can distinguish between these two. How do we distinguish? We have further tests. The first test that we're going to go with is tolerance reagent. Now, tolerance reagent is also known as a silver mirror test. As the name suggests, you're going to form a mirror right inside of a test tube, and it would look like a mirror made out of silver, right? Hence the name silver mirror test. Tolan was the name of the scientist who discovered the reagent. Now, this reagent is an aqueous solution of silver nitrate dissolved in excess ammonia. It is also known as ammoniacal silver nitrate solution. The silver ions, Ag positive, act as a mild oxidizing agent. When warmed, these silver ions will oxidize in aldehyde to form a carboxylate ion. Now, since they are oxidizing something, they will get reduced. All right. Under the alkaline conditions in the test, any carboxylic acid formed is immediately neutralized to a carboxylate ion because we have excess ammonia solution present. So of course, it would H positive is removed and a salt is formed. Since this is a redox reaction, the Ag positive ions get reduced. What do they form? Silver atoms. These silver atoms inside of a tube form a proper mirror, giving a positive test. That's how it's going to go. A completely colorless solution will form an entire layer of silver, so much so that if you hold it closer to your face in a lab, it would act as a mirror. A really fascinating reaction. Remember, there is no change observed when a ketone is formed with tolerance reagent, which means this test is going to go positive and form a silver mirror with an aldehyde, but not with a ketone. So the ketone, a colorless mixture, remains in the test tube. There is no redox reaction. Remember, tolerance test is a redox reaction. Ag positive ions are the oxidizing agent. Aldehyde is the reducing agent. Aldehyde is oxidized to carboxylic acid, which is later on turned on into a carboxylate ion because of the presence of an alkene there. The Ag positive ions themselves reduce into Ag atoms, which form a silver mirror. There are even questions in MCQ portion about this test being a redox reaction. So yeah, that would act as a redox reaction. The second test, and again, it's a test for an aldehyde, is with Felling solution. Felling was also the name of the scientist. Felling solution is an alkaline solution. It contains copper 2 ions. Okay, a quick note about the lab. In lab, we prepare Felling solution fresh. Now, Felling solution fresh preparation requires a lot of hard work. So what we do is that in lab, you'll find Felling solution A and Felling solution B. We don't mix them all the time in the lab. We just mix them right before we are about to use them. So for lab, you'll have both of these separately. You mix them right before your reaction and use them as made fresh. So Felling solution, and in this case, this means that what he's talking about is A plus B together. It's an alkaline solution of containing copper 2 ions. Now, when warmed with an aldehyde, the copper 2 ions react as oxidizing agent. Again, aldehyde is oxidized to a carboxylate ion. Again, an alkaline solution, this means it would be oxidized to carboxylic acid, but since the presence of the alkali, Carboxylic acid would be converted into a carboxylic salt, which means the carboxylate ion. Of course, Cu2 positive would get reduced. They don't get reduced to copper, they reduce to Cu positive ion. This is the first time you are noticing copper as showing +1 state. Now, the clear blue Fehling solution turns an opaque red or orange color, this kind of appearance, with the precipitates, which means there was an aldehyde present. This is the start of it before, and this is the after in case of a positive test. Again, this only goes positive with aldehydes. Ketones are not oxidized. The Fehling solution remains blue, just like the copper 2 blue color that we usually see with copper sulfate. This is copper 1, not copper 2. All right, this gives the idea. Now, you must be thinking that why do we have both the tests as aldehyde test and no a ketone test? That is right. There is no ketone test in A level. The ketone tests do exist. I'm not saying they don't exist at all. We have many ketone tests. We have one coming up, but in case of lab, that's what you're supposed to do. What do I mean by this? I mean that you are supposed to start off with this 2,4-D and pH test. That would clarify either it's an aldehyde or it's a ketone. Now, right after confirming with this orange-red precipitate with 2,4-D and pH, you can do either of these tests. You can either go for a tolerance reagent and have this test positive. If this comes positive after a 2,4-D and pH, it was an aldehyde all along. If this comes as negative after 2,4-D and pH positive, that means that is a ketone. So for aldehydes or ketones, we can never find them out in one test. We have to go for two different tests, especially for ketone. For aldehyde, if you are directly going to jump to the conclusion, you can go for a Tollens or Fehling test. Again, if 2,4-D and pH is confirmed and the solution remains blue, that's a ketone. If 2,4-D and pH is confirmed, the solution turns orange-red or orange simply or red, it means it's an aldehyde. That's how it works. All right. Any questions so far?